try and talk you through about Java 8 library design, highlight some of the things that differ. I'm sure most of you are aware of the features, but I will just run through them as well. Okay, so, yeah, Java 8 was a major update to Java. In terms of the language features it added, Lambdas is quite a big one. So we've got new features of Lambdas, streams, methods on interfaces, which I rather like, and the date and time library. So I'm not going to talk about date and time library in this talk, because I'll be talking that out in 2 hours' time. So I think that if you're using Java 8, you need to kind of rethink elements of how you code. There's enough new stuff in there that can affect coding conventions, design, style, and it's good to have an appreciation of those new design options and what you might do with them. So for the way of having something to talk through, I'm going to talk about Strata. So I work for OpenGamma, which builds open source software for the finance industry. So if you do work in finance, come and talk to me later about finance stuff and I'll take you through Strata in more detail. But basically, the goal is that it provides valuation, risk calculations for those financial instruments you may have heard on the television, things like interest rate swaps, FRAs, credit default swaps, and other similar instruments that maybe crash the world. So it was a greenfield project in Java 8, in effect. Although there was code that did similar stuff before, the reality is that Strata was rewritten from scratch, so it adopts Java 8 style all the way through. Took about 2 years to write, so in essence you're getting wisdom, maybe, of that 2-year experience. And overall, I think, I'm trying to say it's probably quite a good example of, a typical business type application, a typical library certainly, that's written in a Java 8 style. It's all open source if you want to go and look at it. So we're going to talk about Lambdas, we're going to talk about streams, immutability, interfaces, new abstraction techniques, optionals, and a couple of odds and ends at the end. So Lambdas are kind of the headline feature. They are, in a way we had them before with the non-homogeneous classes, but because they're so much easier to write, because they're so much shorter, you can use them in places that you would never have done with anonymous classes, and that makes quite a big difference. So when you have a Lambda, it's always assigned to a functional interface. A functional interface, that's just an interface with one abstract method. So there's not anything fundamentally unusual about that. Same interface as we've already had there, but it only has one abstract method, and then we can call it a function interface. What was new is this concept of target typing. So the context in which you use the Lambda determines what the type of the Lambda is. And that target typing is unusual. It is, it is a new thing. Java didn't really have that before. So what function interfaces have we? Well, we had loads before. We had runnable, comparable, callable. These were functional interfaces that we already had in Java 7 and before, but Java 8 added lots more. So if you're using Java 8, it is important to understand the Java util function package and the various function interfaces that are available there, function, predicate, suppliers, consumers. If you are writing your own function interfaces, well, first of all, consider if one of the standard ones will do. If you want to write your own because a standard one doesn't cover it, there's actually a sort of naming strategy for these interfaces within the package Java doc of the Java util function package. So yeah, if you're writing your own, and we have some of our own in Strata, there's a naming strategy for how to name them. So, what is a Lambda? Well, this is the kind of code we had in Java 7. We've got loading up a list of people, and then we're sorting them on their names. But using that anonymous in the class is very verbose, when realistically, that's the only bit of code in there that actually matters. So if we take away that code, and we add in something new, the Lambda pointer, what we now have is a Lambda. Nice simple conversion from anonymous in the classes to a Lambda. But we can go further than that because we can actually take out the person, because that can be inferred as well. So we can shorten it down to something really nice and short. And we can shorten it again, because there's now a sort method on list that will take a comparator. So all those lines of code just disappear away. And whilst removing code for its own sake is not necessarily a good thing, Java has on occasion been overly verbose, and so removing some of that verbosity is definitely a good thing. And because there's less code to write, you'll write your code differently as a result. So my advice is generally just use lambdas wherever they are appropriate within your system, and they will mostly just work. Now, sometimes you'll find a case where the target typing won't work. So you might need to add back in the type of the types in the parameters. So where we've had that person P1, person P2, there will be occasionally cases where you need to remove that. You'll need to put back that type. And if you have problems, another way you can address it is to extract out the lambda to a local variable and fix up the types that way. Basically, the compiler in Java was never designed to do target typing, and so that they've been able to fit it in at all is great, but obviously sometimes it won't get it right. So streams was effectively the major API change that went along with lambdas. So it follows the observation that a lot of streams have a similar shape, that they're all essentially, doing a lot of the same job. We can consider these effectively to be like design patterns of streams, design patterns of loops. And the stream library is providing a way to abstract this, with the lambdas doing the interesting bits. So here's a typical piece of code that you've probably written many, many times in Java 7, where we're looping around a list. We use an if statement to check something, and then we act on the things that we've checked for. And that's a pattern. It's something you write again and again, and streams offers the potential to abstract that out. So within that code, those are the only interesting bits. The rest of it is effectively a kind of noise. So let's take those interesting bits out, and then we can take the set of trades and we can stream them. We can check that they are active using the filtering mechanism, and we can convert them to that present value money using a map. And finally, we can get them back into a list again by collecting them. So I'm only showing you a small amount of what that streams API is capable of. There's reduce, there's flat map, there's lots of other stuff in there. And those collectors can get quite interesting. If you use Guava's immutable list, for example, you're probably going to want to have a collector that converts to an immutable list as opposed to a regular list. And in Strata, we use immutable list everywhere, so we have written a collector. So if you want to have one, go and find it in Strata. You don't have to write it from scratch yourself. So one of these key goals in streams was to allow for simple parallelism. The idea that we're going to live in a multi-core future, that we need to be able to run our code on multiple cores to make it to go any kind of speed in the future. So the idea of this streams API was that one change makes it run in parallel. So we take our stream, we plump it over to parallel stream, and magically it's in parallel, and magically it's going to go faster. Well, concurrency parallelism is rarely that simple. So in the whole of Strata, we don't use parallel stream anywhere. I do think you have to use it with great care. The number of use cases where it's actually applicable is quite small. You need to have a use case where it's doing lots of computational stuff in, just on CPU. It's not intended for calling out to things like file systems or URLs. Why? Because it's only a single thread pool, and if you block that thread pool, you're blocking, everywhere in your system that uses parallel stream. So you've got no control over that executor. I think there's a case to say maybe the API shouldn't have had parallel stream in it, and that will be controversial to some people. But the use cases for which parallel stream actually applies turn out to be pretty small. What about maps? Well, because Java doesn't have value types, the JDK authors chose not to include any means of streaming over maps. So it's quite a pain to use the existing Stream API to stream over maps. You can do it. You can stream over the entry set. So you take your map.entryset.stream. That'll work, and you'll get a stream over map.entries. But it would be nicer if there was an actual interface called mapstream. So in Strata, we've written a map stream. There's also one in Joule, and I'm sure there are other ones out there. And basically, they wrap up the existing Streams API in something that better handles maps for you. And if you are going to use the Stream API with maps, you'll find it a lot easier to do and a lot more pleasant to use if you have a map stream of some kind. Either copy it or depend on it. So here's our example that I tweaked from before. So instead of a list of trades, I've now got a map of identifier to trade, and I want to output a map of identifier to money. So here I'm using the map stream from Strata, and basically, instead of using filter, I'm filtering on values, I'm doing filter values, and instead of just doing map, I'm doing map values. So what those two methods are doing is basically doing the filter, but only on the value part of the key value pair, and then doing the map, but only on the value part of the key value pair. And that makes the whole API a lot more easy and a lot easier to use, because without that, you'd have to manually recreate an entry, a map entry from scratch, which is very painful. Exceptions in streams. So the for each loop is a language feature. So with a for each loop, you do for each, and then within you do another for each. You kind of know what you're getting. It's a low-level language feature. But streams are implemented as real methods. So if you go to the JDK, there's a whole set of classes that implement that stream library that we're looking at. If you think about all the method calls we just made, we made a call to stream, followed by a call to map, followed by filter. This causes a big difference in stack traces. Something to bear in mind. So here is the stack trace, don't expect you to read it, of one stream within another stream. So goodness knows how many lines that is. It's probably 8, 9, 10 lines for each stream operation. Now, here is the stack trace of a for each loop within a for each loop. It's clear which is more pleasant if you're getting stack traces out of your system. So be careful with streams. They are not always more readable than a loop, and the exceptions certainly are worse. So what we settled on in Strata is essentially that we use streams for small localized pieces of logic. So where we've got a local collection object, and we just want to do some transformation on it, and it's local, it's not calling out to any other big part of the system, it's local and isolated, that's where we tend to using streams. But where we're doing the top level processing, we tend to prefer to use for each loops, even if that's a bit more hassle, because we want to have nice stack traces. So within Strata, in essence, what you have to do is you have to loop around all the trades to calculate numbers, the numbers that you care about. And because that's a top-level loop, we write that top-level loop to loop around trades as for each loop rather than as a stream. Immutability. So yeah, there are lots of tools for concurrency in the JDK. And as we've just seen, parallel stream makes it quite easy to flip between a non-parallel and a parallel stream. But that parallel code, it's not that simple to get right. It's easy to come up with race bugs and check then act bugs and other similar bugs with concurrency. Now, here I am using a stream, just as we saw before. We're checking to see if the trade is active, and if it is active, we're calculating the present value. Now, if that trade object is a mutable bean, then, if some other thread is modifying it, what you have there is a check then act bug. You're checking to see if it's active, but then between the check and the present value call, something may have changed. It may cease to be active. Now, this is no different to what we had before in Java 7. This is the same problems that we had before, but it can be a bit more hidden. The Stream API, because it can be so easy just to hook into, it might not be so obvious that you're doing this. And obviously, with you're using parallel stream in there, things could get more interesting again. So we've taken the opinion in Strata that, it's time to use immutable data objects everywhere. Because threading bugs are fundamentally about that shared mutable state. If you take away shared mutable state, you take away probably the majority of bugs to do with concurrency. Now, the question is, how do you create these immutable beans? So technically, what you need is a final class, so no subclasses. All the fields need to be final, otherwise the Java memory model won't work properly. Basically, if all the fields are final, then when it's constructed, everything is properly locked down. If you don't make them final, they're not properly locked down. The field types themselves need to be immutable. You can't expose a Java util date because that itself is mutable. So you'd be making your bean mutable if you did. And you should be using factory methods and builders, not constructors. Now, I don't know how many of you have ever read the Joda-Beans spec from about 18 years ago. It's quite amusing reading it these days. I wrote a blog post on it because it is so out of date, and it talks about components and gluing them together in swing libraries and so forth. It doesn't correspond with what we use beans for, where we use getters and setters. So really, we need something that replaces that. But IDEs today are only helping you to write mutable beans, so we need this better tooling that will support immutable beans going forward. Now I'm highlighting these three tools as perhaps being the ones to look at. So auto value comes from Google, and immutables.org also is another one, and both of those are annotation generators. So you add, essentially you add annotations to things, and the annotation processors, which you set on the command line when you're compiling it, will generate code for you. Joda-Beans is different. So Strata is using Joda-Beans, and Joda-Beans, as you might have guessed from the word Joda in there, is a project I wrote. So hopefully, yes, there's a slide on Joda-Beans. So with Joda-Beans, this is the code you have to write to create a bean. So you specify its @bean definition. You do implements immutable bean. Joda-Beans will also generate mutable ones as well as immutable ones. That's your choice. And then the fields. So I'm just saying private final trade ID, private final local date trade date, and I'm annotating those with proper definitions where I'm specifying some extra stuff. In this case, I'm specifying that they must not be null. And when you press, when you do the generation, what you will get within the same source file is a block that starts auto-generated start, finishes with auto-generated end, and within that it'll contain all the getters. It will contain a builder method, it will contain equals hashcode toStrings, and it will contain properties just like you see in C#. Well, at least the closest approximation we can get to properties you'll see in C#. So I don't know whether you've used C#, but in C#, you can treat properties, i.e., as a meaningful unit within the class that sits above fields. And once you have properties, you can build things like serialization frameworks on top of that very easily. So Joda-Beans comes with its own XML, JSON, and binary serialization. Now, because all the code that gets generated is within an auto-generated start to auto-generated end block, it means you can add your own code into that bean outside of that block, and you can regenerate it anytime you like. And with Eclipse, when you press, when you just do save, Control S, if you've got the Maven plugin set up for Joda-Beans, then it will regenerate the bean on the fly for you. Doesn't do that in IntelliJ. That's just because somebody needs to write an IntelliJ plugin that does it. It's not hard, but nobody's actually done that. What does it look like to use it? Well, it's a builder, as you'd expect to see. You probably have used them on immutable classes. They're just a pain to write. So tradeinfo.builder, .tradeID, set the trade ID, .tradeDate, set the trade date, .build, and I've got my tradeinfo object. And I can use the generated getters nice and easily. So it takes away the pain of using immutable objects. And because it contains the properties part, it also means you've got all the right tools present to plug into frameworks that need to be able to create these beans themselves. So all the right tools are there for that. And here's an example of what that framework might look like. So here I'm taking that tradeinfo object and I can get a meta bean, kind of like the equivalent of the Java lang class object. And then I can loop around the properties within that. And I can get the name of the property and I can get the value of that property. Now, you've probably never written a serialization framework, but fundamentally that's what they want to do. They want to take a bean and abstractly get at all the properties in that bean. And when you're going the other way, they want to be able to take a set of properties from the serialization format and pass them into a builder and then build the object at the end. So with Joda-Beans, immutable and mutable beans are abstracted out and can be operated in exactly the same way. So your framework doesn't need to know whether something is mutable or immutable or do any special reflection code. There's no reflection needed. So with this tool, you need a tool. You can't just do this manually because it'd be far too boring. We use immutability everywhere in Strata. So all of our data objects are immutable. That means we don't have to worry about threading. We can say to our users, our library has immutable objects. You're not going to see any problems as a result of that. But an impact of that, remember I said beans have to be final, have no subclasses. The corollary of that is effectively no abstract superclasses. So instead of class hierarchies, you want to be using interfaces. So we have a hierarchy of interfaces on top of a single layer of concrete classes. So no abstract classes, just a single layer of concrete classes at the bottom. So here, my interfaces are coloured bluish up at the top, and my classes are coloured orangish at the bottom. So I've got trade interface, a product interface, resolvable trade, a product trade, resolvable trade. So that's my hierarchy of concepts. And then I have individual classes at the bottom that implement those. And I don't overly care if sometimes there's the same fields repeated in those concrete classes. Because Joda-Beans is generating so much of that code for me, it doesn't matter if that has to get repeated. It's not cut and paste, it's generated. Now, obviously in Java 7, if you use this kind of stuff, then you can't have any abstracted behavior. But in Java 8, you can have methods on interfaces. So concrete classes with no hierarchies, and that interface is the hierarchy. And it is those methods on interfaces that make this a viable pattern and a viable design approach. So what we say in all the Strata classes that are interfaces, we basically say implementations must be immutable and thread-safe beans. So if you have an interface, it can't insist that its implementations are immutable, but you can make the Java doc insist it, and then if somebody disapproves of the Java doc and doesn't make it immutable, well, that's their fault, not ours. So better look at those interfaces a bit more. So we have two key changes to interfaces. We have default methods on interfaces and static methods. So a default method is just like a normal method on an interface. The only difference is you have to put the default word in there. So now we have methods on interfaces. That's nice. You can't have a default method for equals hashcode or toString. That's a bit of a pain, but hey, we'll live with it. You can also have static methods, just like a static method would be on a class, except it's now on an interface. Together, those two things give us a lot of power that we did not have before. And in design terms and architecture terms for software, it's these methods on interfaces that are more important than Lambdas. Because the interfaces are part of your macro design. Lambdas and streams are part of the low-level micro design, how you code within a method. Interfaces are about how you design across a system. So it's really important to think about what do default methods and static methods on interfaces, how do they change the way you should think about doing that design? In essence, this is the core part of the talk in many ways. So we use default methods and static methods liberally because we appreciate the importance of them. So let's run through an example to show how this might affect things. So we have an interface called holiday calendar. The purpose of the holiday calendar interface is to say, is a date a holiday? That should be public abstract Boolean is holiday, but let's imagine the Booleans there, shall we? Okay, so we got this nice interface. What we also need to be able to determine is the date a business day? So rather than needing to have all of our classes implement that, or rather than needing to have an abstract method on the interface, to which we also have to implement, we know that is business day is the opposite of is holiday, so we can add that to the interface. So now our interface has become more powerful, but implementations still only have to write the one method. Similarly, we could add a method to our interface that says, find the next business day. So given a date, what's the next business day? There's the implementation, get the next day, is it a holiday or not? If it is a holiday, then keep on going. Nice simple implementation. So now our interface actually has 3 methods on it, but implementers only need to implement 1. That's a good thing. It also means that if you want to come along later and add methods to, you can. The only restriction fundamentally is that the methods which are default methods need to depend on methods that are abstract methods. They can depend on other default methods, but they can't invent stuff out of thin air. What about the static methods? Well, these can avoid things like holiday calendar factory. Java has on occasion been notorious for factories and factories of factories and providers and suppliers. It'd be great if we could remove some of those factories. So here, on my interface, I've got a static method, public static of string ID, which should be returning a holiday calendar. Apparently I didn't do return types when I was writing my talk. So here, it's a static method where I can give an ID and get a holiday calendar, and I didn't need a separate class like holiday calendar factory. So using this will be exactly as you'd expect. So I can get my holiday calendar, holidaycalendar.of.dkco, which is the Danish Copenhagen code in FPML. And once I've got that holiday calendar, I can call the next method, which is a default method, and you'd never know whether it was a default method or an abstract method. You just wouldn't know the difference. Great. So effectively, for most use cases, an interface is now going to act as an abstract class. So when do you need an abstract class? Well, pretty much never, would be the general advice. The only time you would really need one is if you wanted to have abstracted state. So if you want to have an abstract class that has a field string name, and then have a subclass that has another field, string ID. And now you've got the 2 fields there. But that kind of separation of state between those 2 classes, that's generally a bad idea in general. It's much better to concentrate all the state in one class and just to use the interface to abstract over the 2. Now there are limitations on interfaces, so all the methods have to be public. You can't have a private method on an interface. That's unfortunate. Maybe that will be fixed at some point in the future, but there are usually ways you can work around that. The fact that you can't have private methods is not an excuse to write an abstract class. Try and stick with interfaces if you can. And again, the interface will typically act as a factory. So if you have static factories, type singleton type factories, then you can use that pattern of static methods on those interfaces. Now, singletons, everybody hates singletons. Well, no, you don't have to. There are cases when singletons make perfect sense. Some things should just be fixed when you start up your system. And by the way, although I used holiday calendar in this example, holiday calendars in Strata are not actually fixed at startup, but it was a good example to use. So now's the question. If you have an interface that defines your public API, that interface can have lots of nice methods on it, and that interface can provide the ability to create instances of that interface through the static method, can the implementation be package scoped and hidden? And what we found in Strata is that a lot of the time it can be. A lot of the time there is no longer any need to have both the interface and the implementation be public. You can package scope the implementation and have the factory method that creates the implementation on the interface and all the rest of the public API on the interface, and you've reduced the size of your API. And that's a really good trick, a really good tool. And that's where I say methods on interfaces can quite radically change how you think about your design and how users access it. Now, I happen to think that now we have more than one type of methods on an interface, we need to be a lot clearer about what those methods are. So in Strata, we use public static, public abstract, and public default on all methods in all interfaces. Now, the JDK allows you to omit public from all of those. It allows you to omit abstract as well. But I find it quite confusing to see a method that, the abstract method not having a keyword on it, and the default method does have a keyword, and the static method does, and you worry about, are they public or not? There's also another use case where potentially in the future there might be private methods on interfaces. So again, putting public on there now will not hurt you. I believe that this is what should be considered good coding standard practice. Now we have methods on interfaces. Okay, abstraction. So Lambdas are providing better code abstraction. So imagine you have two big methods that are pretty much identical, except for one little bit in the middle. That's what Lambdas are great at abstracting for. You use the lambda to express the bit in the middle, and you pass the lambda to the method. So in our case, we had an example here. So Strata produces lots of measures. So measure is just a number, typically, the value of something, or how the value might change over time. You don't need to understand what a measure is. It's just a number. But each of those calculations of a measure is wrapped in the same code. And we want plumbing in a measure to be easy. So let's use lambdas as method references to do this. So here's our code that we've got here. So we're calculating. We're passing in a trade that we want to calculate some things for. We're calculating the set of measures that we want to calculate and some market data. So what's the value of stuff out there in the financial markets? So we're going to loop around those measures and build up a hash map. So here, in the next method down, we take just the one trade and the one measure, and here we're going to calculators.getMeasure. So given this measure object, the thing that we want to calculate, go and get me something that will calculate it. And that's the abstraction. And here's the key bit. So up at the top of my class, I can set up this calculators object to be a map, which is just a map from the measure name to the piece of code that implements it. So those things there, calc : present value, that's another way of writing a lambda. It's called a method reference, and basically it's just a pointer to a method. So what this code has achieved is basically to say, when they request the measure present value, then you're going to run the code present value. When they request PV01, they're going to run the code PV01. And so as you can imagine, adding a new measure is just adding a new line into that hash map. We didn't have to write all the other boilerplate code that goes around it. And that can be a great saving in some use cases. Optional and null. So there's a new class called optional, added in Java 8. It's for things that are, well, optional. It polarizes opinions. If you go to the internet and you write a blog post about optional, you'll get 6,000 comments in return where everybody will express their own personal opinion as to how you should use optional and how you shouldn't use optional, and it's the savior of the universe or it's completely useless. Yeah, I think used pragmatically, it can be very useful, but you do have to apply some thought as to when and how you use it. Fundamentally, it's a simple enough concept. It's an object that has two states. There's the state of it contains something, and there's the state of it's empty. So if it contains something, that something is not null, by the way. So a something that exists versus an empty is very similar to a variable that is there or null. Very similar concept to null. So here's the code we might have used if we were using null. So in our library code, we have a method called getValue, and that returns a foo, and well, the foo might be null if it wasn't found, and so I have to say, well, if foo was equal to null, then let's default the value of foo to something or throw an exception, whatever's the appropriate thing. Here's how the code looks like if we're using optional. So here we're using find value with the key, and that gets us back an optional of foo. And then on that optional of foo, we can call the method or else, or we could use the method or else throw to process a result. So there's no more checking, not equal to null equals null in that piece of code. It is neater. The API has told you, when you call find value, it's telling you that you need to consider the use case where the thing wasn't found. So it's effectively self-documenting and self-supporting. The rules around using optional, well, the first and most important rule is if you have a variable of type optional, it must never be null. Like never, 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 ever, ever, ever be null. Do not ever have a variable of type optional that is null. You need to prefer the methods like map and or else on optional when you're processing it. There's a method called isPresent, but that's little different to using not equals null. Now, there are use cases where you have to use isPresent. Typically, they're to do with where you want to have an early return from a method, and you can't use a lambda to do an early return. So you need to use isPresent for that. But in general, you should be trying to use map and or else. Think of it something like 70, 80% of your use cases should be or else, and only 10% should be isPresent. So in Strata, we come up with a pattern around the use of optional. So let's say we have an interface, and that interface has a method that is abstract called findValue returning an optional. We can then have a default method called containsValue that calls findValue and then calls the isPresent method on it. And we can have a method called getValue that calls findValue and throws an exception if it's not found. And that gives the user the choice: do they just want to check for the existence of something, get it and have an exception, or process the error themselves? And I think this is a really useful pattern, and it fits very well with methods on interfaces. So it's the ideal kind of thing that you're going to have, if you're looking up data in some kind of underlying storage system, whether that be a database or something, hash map, who knows what. So since optional is a class, it has memory and performance cost associated with it. It was deliberately chosen to not make it serializable. Therefore, it is not an ideal thing to be an instance variable. This is where the controversies tend to come in. The JDK authors added it for the purpose of use in return types. They did not add it for the purpose of use of passing things in as parameters. They did not add it for the purpose of it being stored as an instance variable. You can do those things. However, it was not intended that you should do those things. I personally find that if you use it in parameters, it's often very annoying for the caller, because they will typically just have a string. They won't have an optional of a string. Therefore, they have to wrap it in an optional just to call your API. It's not usually very friendly. So using it just as a return type, that is the best value for the concept in Java 8. and Java 9, but maybe when we come to Java 10 or 11, that advice will change. When we have value types and there is no cost associated with an optional, that's the time to revisit it and potentially use optional everywhere. But given this, the Strata library has no exposed nulls. Now we have the advantage of being a greenfield system. We have the advantage of designing it from scratch. But what we can say is that if you call any method on the Strata library, you will not get null back. Therefore, you do not have to think about checking for null. You're just not going to see it. If there is something that is optional, you're going to see an optional in the return type and have to process using that as well. And as just described, pragmatically, we will use null inside a class, but only within that single compilation unit are you going to have to worry about checking, is it not null or not? In essence, the getter does if field, it does optional.ofNullable, which basically says if the field is null, return optional of empty, otherwise return optional of the thing. And funny enough, Joda-Beans has a nice annotation you can do, which is at property definition, get equals optional, and it will set that up for you. So again, Joda-Beans helps you to write and follow this pattern. A few odds and ends. Don't try and use anything earlier than Java SE update 40. It'll drive you crazy. Basically, there were lots of bugs in the early versions with tighter inference. It's not worth it. You'll still get issues today where Eclipse and Hotspot compile things differently. It's just the nature of it. The spec is very complicated, not always perfectly written, and so you do get discrepancies. This is the bit that should have been in the talk earlier about JDK 9. So Java SE 9 will remove access to some JDK modules. So if you're using sun.star, com.sun.star, com.oracle.star, and various others, in Java SE 9 you won't get access to those classes anymore. You can use a command line flag to get access to them. There'll be certain other workarounds, but fundamentally it's time to start thinking about it because Java 9 is on the way. Java 8 can reflect on parameter names. So there used to be, there is a jar file utility out there called paranamer that allows you to get at parameter names. With Java 8, you don't need to use that external library. The JDK can do that for you. However, it is not enabled by default. They considered it to be a security risk to release parameter names by default. So therefore, when you're compiling your code in Java 8, you have to specifically request, please include the parameter names. But if you do that, then they are available. And there are certain libraries which can make use of that information. We're talking about glue libraries that allow you to glue things together by name, can make a lot of use of the parameter names. And checked exceptions. So all those stream stuff, they didn't deal with checked exceptions at all. They only deal with runtime exceptions. I mean, checked exceptions are such a dead, stupid concept at this point that it'd be nuts easy if they just died. But unfortunately, that's not seems going to happen anytime soon. But what you can do is you can write a nice little utility class. So we've got one in Strata. There's another one in Joule that basically do pretty much the same thing. Ours is called unchecked. And you can pass in a block of code to unchecked. And if that block of code throws a checked exception, it will get converted to a runtime exception. So we pretty much don't have try catch in Strata to catch exceptions. We always use unchecked to do that conversion. It means we get consistent conversions. So they've actually added a type called unchecked IO exception in Java 8. So our unchecked wrapper basically says, if I catch an IO exception, then throw an unchecked IO exception. Otherwise, throw a runtime exception. It's a consistent way of looking at it. In summary, there is lots of good stuff in Java 8. But yeah, design and coding standards do change. There is a lot more potential to abstract stuff. I mean, abstractions are good, except when they're not good and they get too much. So again, be careful, don't overuse it. But focus in on methods on interfaces. Focus in on methods and interfaces, the default methods and static methods, and what they can do for your code, and the ability, in particular, to make your implementation classes package scoped. And reviewing the Strata stuff, we have chosen to use immutable data objects everywhere, for which you need a tool like Joda-Beans. We use static methods on interfaces and package scoped implementations. We do make use of the abstractions, but we are careful around stack traces with streams, because they do get too big if you use them too high up the stack. And we use our optional pragmatically, so that null is never returned from an API, but we don't store optional in instance variables. And yes, if you do work in finance, take a look at OpenGamma Strata, come and talk to me about it. It contains all the stuff that you need to know. And if anybody here knows anything about the CIBOR index in Danish, the Copenhagen Interbank overnight rate, I'd like to talk to you about what the conventions are. Thank you very much. Any questions? Yep. Okay, so yeah, should you do you need the interface? When should you have the interface or just the concrete class? So we would only add the interface where it's adding value. I certainly wouldn't have an interface all the time. The Java time library, again, you should focus on the concrete classes. You shouldn't focus on the interfaces there. There are times when interfaces make sense if you need that hierarchy, if it adds some value. But certainly in Strata, most of the time you'll actually deal with concrete classes for the trade representations for the data side. But when you're dealing with market data, that's when you need much more abstraction, because you need to be able to say, well, it might come from here, here, or here, and that's when interfaces make much more sense. So yeah, I kind of agree with what you're saying, basically. Yeah, use them sensibly. So why do we insist on having our immutable objects be final? The first reason is that they're not really immutable unless they are final. Because if it's not declared final, somebody can come along, write a subclass. That subclass can have a mutable getter and setter on it, and you can pass that object around into a method that is expecting something to be immutable, but you're passing in a mutable subclass. So for strictness concerns, you have to make it final, otherwise you're not protecting yourself against evil actors or stupid actors. Most of the immutable patterns will recommend you to write it final anyway. You only really need the fields to be final to be properly immutable, but most of the advice is that you should make your classes immutable as well. Where I think you were talking about was on our interfaces. So our interfaces say you should make your implementations of this interface be immutable. And I said, if somebody doesn't make it immutable, well, that's their problem. And that's fundamentally because an interface cannot insist through the Java compiler that its implementation is immutable. So a java.comment is the best you can do. And if somebody doesn't obey that java.comment, well, they're not implementing your spec, and it's their problem, not yours. Yeah, so certainly for our domain, we feel that finance, we're guided by standards like FML, where you kind of know the information you need. It's not likely you're going to need extra information. In a couple of places, we have a hash map, which is an extendable hash map where users can stuff anything they like in there. So we have fixed known extension points. I'd also say that an alternative to subclassing something is composition. So if you look at basically the idea is that you write a class that has your additional stuff in it and delegates off to the original class for the extra stuff. And that's how I would expect things to be used in Strata. So if somebody really does need to do something else, I'd expect them to write their class, but delegate off to our class if they need to. So instead of subclassing, it's composition. Okay, thank you. Cheers.